Hello, Dandura girls. Welcome. Okay, here we go. So this is all about energetics. Delta H, exothermic, endothermic. I hope it will make sense. If at some point you don't like it, you don't get it, then tell me. So I'm going to start with sharing my screen, and hopefully it will make sense. So let us just go to. Here. St. Mary's, can you see this, my presentation? Cool, excellent, well done. Cool is a good word to use in energetics because we're talking about heat energy. So here we go. Um, you have all seen fire, and you have all probably used fire to cook. You have used fire to be warm. You have seen the bush burn, all sorts of things, okay? But what I want to do is I want to ask you, what is happening when something burns? Where does the energy come from? If you light a match and you put your hand on it, why? Why does it hurt? Where does that heat energy come from? Can anybody tell me where the energy comes from if you light a match? Because we've all seen it, but where is this energy coming from? This is not clear. So, can anybody tell me? Somebody at St. Mary's thinks they know. Where does the energy come from? Because the match does not contain the heat. Otherwise, when we break the match, it might give out heat, but it doesn't. So a lot of heat comes from burning quite a small amount of wood. If you get a car and you run it for a long time, you have used a lot of petrol or diesel, but it wasn't very much compared with how far you go. Where did that fire come from? Anybody think? Anybody think about what that might be? Because we see flame. Here it is. Here's some flame going. I'll tell you that the flame is particles of unburned carbon giving out light. Okay, that's what flame is. It is the unburned carbon giving out light. So as you have a match, a candle, a fire, when you can see it, the flame is actually pieces of carbon, atoms of carbon, which are hot. And when they are hot, they give out light. That's what we're seeing. But where's the heat coming from? That's where we're going today. That's what we're going to try to do today, is to work out where that energy comes from. Okay. So what I'm going to do is I'm going to move on from this one. To what the energy topic covers, what it has in it. Don't write these down because I'm sure you can get copies of the syllabus. It's not really worth writing this down. But what I'm going to do today is endothermic and exothermic. I'm going to do energy level diagrams, sometimes called energy profile diagrams. I'm going to look at Hess's law, which is a very important law found by a German a long time ago. And then we'll see whether we get to bond energies. We may get to bond energies, we may not. That may be next time. But the whole topic then goes on to cover something called latent heat. And that's fairly simple. And then how you measure, for paper 3, how you measure and calculate energy changes. Okay, so that's what we're looking for today. Okay, so oops, something funny happening. Okay, so here we go. So you know that an exothermic reaction gives out heat. You know that an exothermic reaction gives out heat. So think about an exothermic reaction which you know about. For instance, burning. That is a good example. But if you think, a cup of coffee, That is not a reaction giving out heat. The making it hot in the first place, that was, but the giving out heat of itself is not an exothermic reaction. So it has to be a reaction which gives out heat. Endothermic accept heat. They take in heat, and they take in heat from the environment. Now, the difficult thing about this for some people is realizing what this means for instance, the thermometer. So if I put a thermometer in the exothermic reaction, the thermometer will say the temperature is increasing. Endothermic reaction, if I put a thermometer in this one, the temperature will decrease. Some people get a little bit confused by this, but you have to realize that it is the chemical reaction, the equation, which is giving out the heat, or the chemical equation, which is taking it in. So let's have a look at exothermic and endothermic and what happens in them. The first thing is that in exothermic reactions, heat is given out. Okay, that's the first thing that you need to know. Heat energy is given out. The second thing is that the products are lower down in energy, are more stable than the reactants. We'll see that in a diagram in a minute. You know it anyway, but the products are more stable. In other words, there has been a drop in the chemicals. The chemicals at the beginning at a high energy, and as they drop, they turn into the products. In endothermic reactions, heat is taken in. So if we take an example of a stove and you are cooking some ugali, then the changes inside the pot are endothermic reactions, but the stove itself is giving out. Somebody needs to mute, please. Somebody needs to mute. Guys.
Silver Spring, kindly mute.
And thank you. Silver Spring, we had a small problem last week with it fairly regularly unmuting. Could you make sure it stays mute, please? Thank you very much. Okay, back to the pictures. So heat energy is taken in. So think about a stove, think about a pot on the stove, the heat coming out of the stove, if that's exothermic change, the wood or charcoal burning, or the oil, whatever. But inside the pot, the food which is changing from one type of material into another, that is endothermic change. And this is a funny idea, that the products are less stable than the reactants. In other words, the products which are being made are less stable, higher energy than the stuff you started with. So let us say we are going to do something really simple, like boil an egg. When you boil an egg, the stuff inside the egg goes from very liquid to much more solid. That is an endothermic change. But if the boiled egg is at a higher level, why does it not come back? Well, we will look at that. Okay. Here's an example of an endothermic reaction. It was done at my school. The woman was a student of mine. She makes a mistake because she spills some of the chemical on the desk, but I told her just to carry on. So here we are. Here's a little experiment which you're going to be able to see, I hope, in just a moment. Okay, here we go. So this is mixing together two solids, and solids don't normally mix together very well. They mix okay, but then they can't react because the particles can't touch each other very easily, or the chemicals inside the lump can't get at each other. But it's a very interesting experiment. So it's barium hydroxide and ammonium chloride. You don't have to worry about the chemicals. We're just going to watch what happens. I want you just to understand what's happening here. The little piece of glass at the bottom, the watch glass, has got water on it, and we'll see why the water is there. This is one of the chemicals. This is the other one. They will be added together. She will spill it on the desk. This temperature probe is attached to a sort of screen that we will be able to see in just a minute. So here we go. There, mistake.
Two solids reacting together here, and all I'm going to do is mix them together. Okay, and almost instantly you can see that their state is changing slightly. If you want to go inside it, you can. They're almost clumping together and making almost like a paste.
So the two solids start to react and it becomes much more like a liquid. You will see in just a moment.
Temperature, it's already gone.
Okay, it's gone negative. It was up in normal room temperature, and now it's gone down to -8 already. And in a minute, she's going to test the gas.
So this is an endothermic reaction where the products will have more energy than the reactants. They're taking in the energy from the outside surroundings. So you can see now we've actually got quite a pasty liquid. And we've also got quite a big smell going on. And that's because we...
Now, here's a question. That is a piece of red litmus, damp, which has gone blue. Can anybody tell me what gas that is? Can anybody tell me what gas is? An alkaline gas. It is the only common alkaline gas. Dandora think they know, and they think it's ammonia, and they are correct.
have made ammonia. Now, sometimes it goes over 30 degrees, so we can aim for that. But as you can see now, it's completely liquid. Put some lumps in there. And it's very cold, to the point that I can now pick up the watch glass because the water has frozen.
So the water that was underneath has frozen and stuck the pieces of glass together because the temperature is very, very cold. So -28, that is a very, very cold temperature. And she goes on to show a graph. We're not really interested in the graph. So in an endothermic reaction, if you put a thermometer into it, then the temperature will go down. That is because the temperature, the heat in the thermometer is being taken into the chemicals. The chemicals are reacting together, and when they react together, they are absorbing all the heat from the atmosphere, from the air, from the glass, from the thermometer, which the thermometer says, I'm getting colder. The thermometer tells you it's getting hotter, that's exothermic. Thermometer says I'm getting colder, that's endothermic. Okay, onwards. Everything okay with that? Cool. Silver Spring have no thumbs. That's a shame. Bad luck, Silver Spring. Do you have thumbs, Silver Spring? Oh, you do have thumbs. That's good. Thank you. Sorry. Nice. So we've seen an endothermic reaction. Let's see an exothermic reaction. In this exothermic reaction, this is one from the Royal Society of Chemistry in the UK. This is a mixture of iron oxide and aluminium. And iron oxide and aluminium do not normally react. So they have to start it with a fuse. So they have a little piece of magnesium, which takes the heat into it. And then almost immediately, this happens.
So instantly the thermite reaction starts, and you can see that it's so hot it's burned a hole through the bottom of that terracotta flower pot. But if we go in close now, Brady, you can see all that really quite nice molten iron. Now that's so hot that the iron is...
Let's see it again. So in here iron oxide and aluminium powder mixed together, and a little bit of magnesium is taking the heat into it to start it. And that's an important idea. And then you will see it breaks the pot and comes out as molten iron.
So instantly the thermite reaction starts, and you can see that it's so hot it's burned a hole through the bottom of that terracotta flower pot. But if we go,
So this is molten iron, which is dropping out of the bottom of it. That's a very exothermic reaction. Really quite good. That's molten iron in the bottom there. So the aluminium, being more reactive than the iron, takes the oxygen away from it and leaves molten iron and aluminium oxide. Okay, so that's just two examples, one exothermic and one endothermic. So let's have a bit of a talk about what this is about. This is about changes in enthalpy, because one of the things we cannot do is to measure the energy of a chemical. We can measure the difference between one chemical and another, but not the chemical itself. So change in enthalpy, I'm sure you've come across this. It's given by delta H. Delta H, delta is the capital Greek capital D. It's a triangle shape. So capital D, H, delta H means change in heat energy. Now, when you've got change in energy delta H, then if it's exothermic, heat is lost from the chemicals, and therefore delta H is negative. So we would write an equation which says this chemical changes into that chemical, and at the end, delta H is negative and a number. And endothermic, it's going to be positive. So I need to just ask you whether that is completely familiar with you. So is the idea that exothermic is negative and endothermic is positive, is that okay? Is that something that you already knew? Did you already know that? Or did you not already know that? If you didn't already know that, show, okay, that's okay. So that's a mixture. That's okay. Thank you very much, guys. Thank you. So just try and remember, delta H, triangle H, is negative number if it's exothermic, positive number if it's endothermic. We'll see them in just a minute. So here we are. Okay, so here is an example. This is methane burning. That's CH4 in oxygen producing carbon dioxide and water. And afterwards is written delta H is negative 890 kilojoules per mole. kJ/mole, kilojoules per mole. So for 1 mole of CH4, 1 mole of CH4 weighs 16 grams. Only 16 grams of CH4 will make 890 kilojoules come out. Negative means it is lost, in other words, given out. This is nitrogen and oxygen combining to make nitrogen 2 or nitrogen monoxide. And the number is 181, but this time it's positive. It's positive because that has to be added to it. It's an endothermic change overall, okay? So exothermic has a negative number, endothermic has a positive number. We have some which we call mesothermic, where there is no plus or minus, the energy change is 0. In other words, there is no energy change. The reason it is delta H, because there are some reactions which give out sound, or give out light, or give out electricity, is because a long time ago we invented the thermometer, and we liked the thermometer, so we measure temperature. Most chemical reactions give out or take in heat energy. Okay, so we're now going to move on to energy profile diagrams. Okay, and I want to give you a bit of an idea about this. So here we go. So if I take oops, why is that not working? CH4 and, oh no, sorry. Oh well, and oxygen, and it makes carbon dioxide and 2 waters. and it said delta H is negative 890 kilojoules per mole. Then what does that mean if I was trying to look at what was happening in the reaction? Well, I can draw a little graph which shows me the energy up the side. For those of you who don't know these from before, that's okay, just watch. And along the bottom, some people put time, but most people put progress. Don't worry drawing it just at the moment, just try and concentrate just for a minute, because I will show you a better drawn one in just a minute. Now, if 890 kilojoules is lost from this reaction, it means that at the beginning, the CH4 and 2O2s must be higher than the CO2 and H2O. So what we do is we say, hey, at the end, the CO2 and 2H2O is down here, and we give them levels. We say, okay, that's at that level, and that's at that level. If I take some methane and some oxygen and I just mix them together, nothing happens. I have to add a small amount of heat. So that small amount of heat is shown on here like this. We go, oh, hey, I have to put in, whoops, sorry. I have to put in a small amount of energy, and then I get out a lot of energy and I end up down at the bottom. Okay? And this little bit of energy which I have to put in is to activate what we call activate the chemicals. And that energy, whoops, up to the top there, not over it, not over it. Okay, that there is given the symbol EACT, or sometimes AE, and they mean the same thing, which is the energy of activation. It's what's necessary to start the reaction off. But where's the 890? Well, the 890 is the difference between this level here and the level down at the bottom. In other words, that must be 890 kilojoules per mole. Now, sometimes they show this as like a number like 1000, and then this number down here would be 110. So they ask you to calculate, but that's how you do it. Okay, so that, don't worry if you haven't already drawn this, because I'm going to show you a better picture. But what I want you to do is to get the idea that the drawing has to show that the reactants at the beginning are higher than the products at the end. Okay, the reactants at the beginning, that's the CH4. These are the reactant. Whoops, sorry. These are the come on. Come on. Oh, my pen has gone off. It has decided it's going to do something silly. Oh, look, it's drawing little pictures. Isn't that nice? Well done, pen. So these are the reactants. And these are the products down here. Could it go backwards? Yes, it could, but it would be difficult, because now it has to go up not just the small energy of activation, but it has to go all the 890 as well back up. Okay, let's move on. Here's a better picture. So it's energy up the side, and this is course or progress of the reaction along the bottom. And the reactants are higher than the products, and the total heat change is just from the top level to the bottom one, and that's the energy of activation. Now, the reason we don't include the activation energy is because if this is 0, it goes up a certain amount, then it comes back down to the same point. So all that given in is taken out again. So that's an exothermic reaction. Now that means when we think about an endothermic reaction, the opposite must be true. So let's have a graph. So we have energy, and along the bottom we have the progress of reaction. And in this case, we must start somewhere and end up higher up. So this is an endothermic reaction. It starts with the reactants lower down, and the products are going to be higher up. But what's quite funny about this is that quite often the energy of activation still goes over the level and then comes down to it. And now the total energy change will be from this line up to there. Okay, so that will be the delta H. And because it's going upwards, it will be plus a number like 200, 600, whatever. Okay, so that's an endothermic reaction. The reactants are lower than the products, and we have to put energy in to get up there. Okay? Here's a better picture. Hang on, here's another picture drawn better. Okay, it's the same thing, shows the same thing, but not so bad as mine. So I'll give you a moment in case you want to copy that out. Anybody got any questions? Anybody got any questions so far? We will see quite a lot of these. You're looking very sharp. If you're okay, well done, Dandora. Mathari, Glory, Wamuini. Oh, you're saying no, you've got a question. Okay. Ushirika, you write it down, write down the question, or put it in the chat. Put the question in the chat. If you have a question, see if you can just put it in the chat. It will make it easier for everybody to see. So those are what we call energy profile diagrams, and they're very useful. Okay, if anybody has a question, just either unmute for a minute and ask it, or put it in the chat, or write it on a piece of paper and show me it. Nobody? Is everybody okay so far? Show me if you're okay so far. St. Mary's are going, no, we're not okay. All right. Tell me what the problem is, St. Mary's. We will go into it. I will show you. It will make more sense in a minute. Ah, Dandora Girls has gone. Okay. Okay, I'm going to stop sharing just for a minute. Okay. So people can tell me what the problems are. Yeah, Dandora Girls has gone. I do. Okay. Who has a question? Who has a question? I'll give you an example of something. Some people don't like the idea of things going down and up and so on, but I'll give you an example. If I take this pen and I drop it onto the cover for my, what's it? Hang on just a moment, just a moment, St. Mary's. I will come to you in just a minute. When I drop something, we can hear something, okay? Energy is given out. As things drop, energy is given out. We can hear it. I can feel it in this. Energy is given out. When I lift it up, I have to use energy to lift it up. If I say to the pen, up, come on, pen, up, it doesn't behave. I know this is childish, but it doesn't matter. So it'd be good if it worked, wouldn't it? It'd be good if I could say, get up, pen, and it would just go. But anyway, so I have to put energy in. Just mute just a minute, please. Thank you. So dropping gives out energy. That's the same in heat. When reactions happen, when methane burns, when wood burns, when charcoal burns, when a match lights, heat is given out. And that means that the chemicals have gone down in energy, okay? They've gone down in energy. Wamawini, do you have a question? No, let me just have a look at St. Mary's, because hang on, let me just have a look. Okay. Good question. Thank you for that. St. Mary's said they don't understand progress of reaction. It's just basically saying, where are we in the reaction? So let me just remove that. So where are we in the reaction? So I take my stove, I'm going to cook some food. I put in, let's say I've only got wood. So I'm going to put my wood in, I light it, and it starts to burn. And the wood plus oxygen is turning into ash, which includes bits of earth and so on, but also CO2 is produced and water is produced. So where we are, progress of the reaction means, are we at the beginning with the wood, or are we halfway, or are we at the carbon dioxide and water? Okay, it just means where in the reaction are we? Are we right at the beginning and there is only reactants, or are we right at the end and it's only products, or is it a mixture? Well, Sharika also has a question. So let's have a look at your question. You're going to have to get a lot closer than that. Oh, Sharika, you're going to have to get closer. I can't see it from there. Bring it up. Be courageous. Come on, Oshirika. Oh, it's so tiring to get out. Come on, Oshirika, let's have a look. Do we have a question coming? We have a question. Can we hold it in front of the camera? Can we hold it in front of the camera, please? No? Okay. All right. Does anybody else have a question so far? Anybody else have a question? You can just unmute and ask it if you want. Okay, let's move on. So, in answer to some to the question which we had from oh gosh, I can't remember. The course or progress of the reaction means just where are we? So if we are over here with the reactants on the left-hand side, to start with, we have reactants, nothing happening. And then we light a match or whatever, make it happen. Then we have a mixture of reactants and products, and then it is all product. That is what it means.
Silver Spring, kindly mute.
I have a question.
Okay.
You have a question? Okay, you can ask.
Guys, I'm just going to stop sharing.
Silver Spring, you cannot get to your question. Silver Spring. Right? You can just write the question and then you can show it. In Silver Spring.
What is the meaning of endocrine?
What is the meaning of what?
Silver Spring, kindly mute, then you can write your question.
Right, Silver Spring, that was really difficult to hear, but you said, what is the meaning of? And then I couldn't hear the rest because there was so much disturbed noise. So I'm going to unmute you and we're going to see if you can, or I ask you to unmute and you can ask the question, please. What is the meaning of? Unmute and try and ask the question, please. Silver Spring? Wow. Do you have two microphones there, Silver Spring? Silver Spring, try and write your question and show it me. Wow. can't even mute you, Silver Spring. Oh, that's better. Silver Spring, if you have a question, please write it and show it to the camera, please, because that will make life much easier. But Silver Spring have frozen now. Ah. Let's see if we can see the question which they have. What is the difference between endothermic and exothermic? Okay. We've sort of dealt with that, but I will tell you it again. So exothermic is any reaction which gives out heat. So anytime we have a reaction and we put the thermometer in and the thermometer says it is getting hotter, that is exothermic. Exit, you know, exit is the way out. Therm is something to do with heat energy. So exothermic means giving out heat. Endothermic just means it takes in heat. Okay? All right, let's move on. So exothermic, anything that gives out heat. Okay, here are some examples. I just want you to write down a couple of examples. Probably the best for exothermic is burning or neutralization. They are both exothermic reactions. It is important to know an example. Endothermic, photosynthesis, the production of sugars by plants and with sunlight, that is an endothermic process. So is potassium nitrate dissolving in water. They are good examples of endothermic reactions. Okay, melting and boiling are endothermic changes, but they are not reactions. Okay, so let's look at a question. Here's a question which I'd like you to look at. I will show you how to do it in a moment, but please, everybody, just have a look at it and see if you can do this question. See if you can work out how to do it.
Salad. Alafu ndizi tena tuzipie bakuli ijayo.
I have a question.
Yes, Dandora?
Could you please repeat the examples of reaction of endothermic and exothermic reactions?
An exothermic reaction, the best one is burning or combustion and neutralization. So exothermic reactions, burning and neutralization. And for endothermic, photosynthesis and potassium nitrate, that's KNO3, dissolving in water. Did you get that, Dandora? Okay, good. Sorry, St. Mary's, you didn't get that? That was exothermic is burning or neutralization. Okay, burning or neutralization. They are both exothermic. And endothermic is things like photosynthesis. Endothermic photosynthesis. That is producing energy, producing sugars in plants. I'll show you it again. I'll show you it again in just a minute. But for those people who want to have a go at the question, just have a look at the question now for a minute. So here's the energy levels. Sometimes it's called progress of reaction, sometimes course of reaction, sometimes reaction path, sometimes it's called time at the bottom. It doesn't matter. This is where we start here on the left, and this is where we finish on the right. It says work out the activation energy. You're going to be using the numbers here and calculate the energy change in the reaction. Just have a go at those. And then is it exothermic or endothermic?
Akolama amepiga leo. Amepiga kolama.
Godfrey, kindly mute. Godfrey, kindly mute. Mute Godfrey.
Thank you, Godfrey. So in the question, you can see that we have half a molecule of hydrogen and half a molecule of fluorine on the left. And on the right, it turns into HF, one molecule of hydrogen fluoride. And it starts at 389 and it goes up to 611. And then it goes down the other side until it gets down to 100. So you know what the energy of activation is, because that's the amount needed it to get up to the top, from the left to the top. To get down again, it isn't from the top down to the 100. It isn't from 611 down to 100. It's from where we start. So I'll show you how to do it in a minute, but if you want to show me an answer, that would be cool. I can see some of your answer. Sorry, show me again, please, Dandora. Delta H is negative 511, according to them. What about the energy of activation? Dandora, the energy change for the whole reaction is not 511. Because when we start at 389, we go up to 611 and then we come back down to 389. So we put it in and then get it out. So this is the same level. So the overall reaction is a bit different. I'll give you another minute and then I will show you how to do the question. I'm not expecting everybody to be able to do it straight away, but that's a proper KCSE Form 4 examination. Ah, well done. Well done. Good. Very good. Well done. Let me have a look. Very good. Very good. Well done. Yes. Well done, Osharika. Well done, Osharika. Well done, Dandora. Okay, I'm going to move on because I'm going to show you how to do it. Okay, so here we go. The next slide. Here's the question, and this is what we do. So first, don't write this down, but the activation energy is the amount of energy that needs to be put in to start the reaction. It's this, okay? It's from the initial chemicals up to the top of this peak here. That blue arrow is what it is. We're going to put that in, and then we're going to get it back. So in this case, it is 611 minus 389, which is 222. It's going up, so it's plus. Okay, it's positive 222. So that's the activation energy for the reaction. Now the energy for the whole reaction is from here down. So the heat of formation that's the heat of the reaction, the enthalpy of the reaction, is from the beginning to the end, forgetting the bit where you go up and then come down again, because we come back down to this level, which is back at sort of 0, or back at 389. And therefore, it will be 389 minus 100, which is 289. And because it's going down, it's negative, and therefore it's exothermic. So let's look at the question again. So the energy of activation is from here up to here, from 389 up to 611. So it's 611 minus 389, 222. And that will be positive because it's going up. So anything going up is endothermic. Anything going down is exothermic. So even an exothermic reaction starts with endothermic and then goes exothermic. Then the overall change is from here down to the bottom. Okay, so here we are. That's the activation energy there. And that is 611 minus 389. And then we have the heat of formation is from here downwards, which is the 389 minus the 100, which is negative 289. Okay, negative 289. And so it's exothermic. Okay. All right, so continuing. Even if this doesn't make a lot of sense yet, don't worry, it will start to. Okay, this is about Hess's law. And Hess's law is, we're only going to do Hess's law today, and we're going to see whether we can understand what it is all about. I'm going to tell you what it says. Don't bother writing this down. We will come back to this. I'm going to try and explain it in a more visual way. So don't write that down. So here we go. So I'm going to try and draw a picture. Oh, I might escape this. Hang on. Just going to come out of this just for a minute. Just a moment. I just want to be able to do something. Okay. I will hope I can now share that. Okay. So I'm gonna draw a little picture on here, and I'm going to try and show you what this means, what this whole thing about Hess's law means. Okay, so here we go. So I'm going to start with a reaction which I want to know the equation of the energy for. Oops, sorry, hang on, what happened there? Let's go back. So I'm going to start, come on. I'm going to start with ethene, and I'm going to set fire to it, and I'm going to turn it into carbon dioxide and water, like this. There are 4 oxygens there, another 2 here, so that's 6, so we need 3 O2. And what I want to know is what the energy change is. In other words, I want to know delta H is what, okay? Now, I'm going to draw one of those energy profile diagrams. So here's energy up the side, and here is the progress of the reaction or the course of reaction. And I'm going to tell you that C2H4 is up here, okay? And I'm going to tell you that if you set fire to it and you find this delta H, it's really quite large. And by the time we get down here to the 2CO2 and 2H2O, it has gone up and then down. And it has lost. So from this level all the way down to here, whoops, that's not very straight line, sorry. It is negative 1411. Okay. Now I want to tell you that if I take C2H4 and I first turn it into C2H5OH, that's ethanol, and then I turn it into CH3COOH, that's ethanoic acid. These are two pieces of further organic chemistry you will come across. Then when I make it into this, I drop 45. So it's going down, so it's minus. And when I go down from there to here, I lose minus 206. So in other words, if I take this and I turn, I take this and I turn it into ethanol, it follows that. If I take this and I turn it into that, it turns into that. And I can set fire to this and I can turn it into carbon dioxide and water. And the interesting thing that Hess noticed was that from here, down to the bottom, is 1160. Now, this is not worth writing out on itself, okay? But I want you to spot something, and that is this, that on the right-hand side, the total energy change is negative 1411. On the left-hand side, it is 1160 and 206 and 45. And if I add those up, 5 and 6 is 11, carry 1. 4 and 6 is 10, 11, 1, carry 1. 1 and 2 and 1 is 4. Oh, look, they are the same. This is negative because it is going down as well. So in other words, what Hess noticed was that it doesn't matter how you get there, the total energy change will be the same. So let's go back a slide. If you don't understand that, don't worry. Do not worry. I will explain it in a different way to start with. What Hess Law said is the overall delta H for a reaction only depends on the start and the finish. Only depends on the start and the finish, and is independent of the route taken. In other words, it doesn't matter if you do it in 1 step or 20 steps, the total energy change will be the same. All right? I'm going to stop sharing just for a minute and give you a different example. So, Hess's law says, if I start here and I end here, it doesn't matter whether I go down in 1 or in many different steps, the overall energy change is the same. I want to give you an example. You go up a set of stairs and there are 10 steps and you jump from step 10 down to the bottom. That is a lot of energy. You break a leg, perhaps. Instead, next time you go, I'm going to go down 1 at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each 1 step is smaller, but the same amount of energy total as jumping the whole way. So whether we jump 10 steps or 10 times 1 step, it's the same. And that's the same as doing double steps. So do it down in 2 and 2 and 2 and 2. 5 times 2 is 10. It's the same. So Hess's law says that the overall delta H from the very beginning to the very end depends only on where the very beginning is and where the end is, and doesn't matter how we get there. It's always the same. Now, I know that's a bit hard. I understand that's a bit hard, but this is what he said written down. Okay, this is it. The overall enthalpy change, that is the delta H for a reaction, comes from the difference between the first, the initial, and the end states, the chemicals at the beginning and the end, and doesn't matter how we got there. And my silly, very badly drawn example is this. So I can start here C2H4, and I can go in one leap all the way down to carbon dioxide and water, and that will give me negative 1411. It goes down, so it's lost negative 1411. Or I could try something different. I could turn C2H4 into C2H5OH, a different chemical. And that loses me 45. And then I could turn that into this. This is vinegar. This is alcohol. C2H5OH is alcohol. CH3COH is vinegar. So I can take ethene, make alcohol, make vinegar, and then I can burn the vinegar and it produces carbon dioxide and water. So Hess says it only matters that we are C2H4 at the beginning and CO2 and H2O at the end. Okay. So I'm going to make it slightly, hopefully, but easier. Don't bother drawing this. Do not draw this. What Hess says is that if I start at reactants and I go to products in route 1, that's one step, then the delta H of the reaction is the same as if I total it going a different way, going to some intermediates, some other chemicals, okay? So the delta H for the reaction for route 1 and route 2 is the same total. I'm going to give you a silly example. So here's my one C2H4, and I'm going to add hydrogen to it, make C2H6, okay? I'm going to do something silly, though. I'm going to say, hey, let us go from Nairobi. Let us go from Nairobi to Malindi. Let us buy some tickets. And my Nairobi to Malindi has to go via Mombasa. So I get some tickets. I start at Nairobi here on the left, and I take my ticket and I get my ticket out and I want to go to Malindi, but I want to go via Mombasa. And I show my ticket to the person, the ticket conductor. And I show him a ticket from Nairobi to Mombasa. And he says, yes, you can go from Nairobi to Mombasa. And when I get to Mombasa, I've got the wrong ticket. And I show him a ticket from Malindi to Mombasa. And he says, no, you can't go to Malindi. What you need is from Nairobi to Malindi is either one step or is two steps via Mombasa. And it has to be in the right direction. So Nairobi to Malindi is the same as Nairobi to Mombasa, Mombasa to Malindi. And that's important. You have to get the steps in the right directions. Okay? That's fairly complicated. But if we go back to chemicals, then from reactants to products from Nairobi to Malindi is the same whether we go straight or whether we go via the intermediates, which is Mombasa. Okay, reactants to products, route 1 is the same as route 2 all the way around. Okay, so we're fairly near the end, so this is probably a little bit complicated at the moment, but don't worry, it will get better. But I'm going to make it worse first. Okay, I'm going to make it look more complicated first. So that's my plan, Nairobi to Malindi, and I'm going to go via Mombasa. Okay, I will ask whether there are any questions in a minute. So I'm going to take an example. So don't try and do this, just watch as we do it. We will go through it again next time, so do not try to write it down for a minute. Just try and watch and understand. So we're going to try to find out what happens when we burn methane, okay? That's what I'm going to try and do. I'm going to try and find the data when methane burns, okay? But I haven't got that information. What I've got is some more information, and they have told me if I take carbon and hydrogen and I make methane, the delta H is negative 75. Okay, if I take carbon and hydrogen and I make methane, it's negative 75. If I take carbon and I burn it to make carbon dioxide, it is negative 394. And if I take hydrogen, I burn it, make it into water, it's negative 286. Okay. Now, what I'm going to do is I'm going to try and use these three pieces of information to find out this one at the top. Let's see how it works. So here's the equation I want. CH4 with oxygen makes carbon dioxide and water. I'm going to find out what can be written at the bottom and can be made into both sides. I'm going to then draw the arrows in the right directions. You will see what I mean in a minute. And then I'm going to multiply if necessary. And then I'm going to make sure I'm going from Nairobi to Mombasa to Malindi. You'll see what I mean. So here we go. So here are the reactions which I know that I have been given information for. So carbon plus hydrogen makes methane. So I can write C plus 2H2 down here, and I can draw an arrow from this to methane because I know carbon plus hydrogen makes methane, and I know that is negative 75. I also know that if I take carbon and I turn it from carbon into carbon dioxide, that arrow, that it is negative 394. And I also know that when I burn hydrogen and I turn it into water, let me just move you out of the way, burn it into water, that arrow, that it's negative 286. But look, I'm making two of them, so it's two 286s. So now all I've got to do is I've got to get, remember, from Nairobi to Mombasa and to Malindi. I don't want this arrow to be going in that direction. I want to go in the opposite direction. Okay? I want to go from here. I want to go from CH4 down because across the top is the same as going from Nairobi to Mombasa to Malindi. So I need to change the one arrow. Okay? I need to change the arrow that goes across. So instead of it being in this direction, upwards and negative 75, it has to be going downwards, and that's positive 75. So change the arrow direction and you change the number. So negative 75 becomes positive 75. Okay. So I've got positive 75. Then I've got, from this over here, I've got the 394. I've got two 286s, and that totals negative 891. And therefore, across the top is negative 891. So this looks really complicated, but let me show you what I'm doing. Let's go back, go back, go back, go back. All I'm trying to do is find some chemicals for Mombasa where they go in either upwards or downwards, it doesn't matter, and then make sure my arrows go from Nairobi to Mombasa to Malindi, okay? That's what I'm trying to do. So in this example over here, what I'm doing is I'm changing this one arrow. I have found that from carbon and two hydrogens, I can make methane, I can make carbon dioxide, I can make water. So I put C plus 2H2 down here. I have an arrow up here, which is negative 75. I want to reverse that one, which makes it positive 75. So from this to over to the products is the same as going down and then up, which will be positive 75 and 394, negative 394, and negative 286 times 2, which is where we get the sum positive 75, negative 394, negative 572, which gives me negative 891. That, ladies and gentlemen, is really hard, okay? If you understand that, you are too clever to be here, okay? What I'm doing is I'm showing you now, and we will do it again next week so that you can understand and do it yourself. I am not expecting anybody to understand it fully now. If you do understand it, show me this. If you understand some of it, show me this. And if you don't understand it at all, show me this. Thank you, St. Mary's. Thank you, Mathari. Thank you, Dandora. Thank you, St. Mary's. That's very, very good. Last year, listen, seriously, last year when I taught this to the centers last year, most people went, no. Okay? And so if you are doing this and saying, well, I'm on the way, I may be able to understand this if we do it again, then you are doing really, really well. So let's just go back over what we've done so far. Let me just go back because you've done quite a lot. So here we go. So we started way, 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 way back. And we discovered that exothermic reactions give out heat, endothermic reactions take it in. There is a difference between the types of reactions. And we said a stove, for instance, gives out heat, so it's exothermic. The cooking, the food takes in heat, so it's endothermic. We said that delta H, we saw a couple of examples, a negative exothermic, an endothermic, and we said that the change in heat energy is given the symbol delta H. If it's exothermic, heat is lost, it's given out, it goes out of the exit, so it's negative. If it's endothermic, it's positive. So here were two examples. That's methane burning, it's negative 890, so it's exothermic. Nitrogen reacting with oxygen is positive. It's difficult to do. We have to put energy in, so it's endothermic. We then came across energy profile diagrams. There's the reactants. That's the energy of activation up to there. And then importantly, the difference between the beginning and the end is the total change. Okay, so when we're trying to find delta H for the reaction, it's from the beginning to the bottom, not from the top. And in endothermic, it looks like this. It's all going up, but the activation energy still goes higher, but then it comes down. So the total delta H is from this level up to that. Then we came across a couple of examples, and the best examples are burning and neutralization for exothermic, and potassium nitrate dissolving and photosynthesis for endothermic. Okay, they were just examples. Don't write them all down. There is no need. They are just a couple of examples in case the examination says, give me an example of an exothermic reaction. Give me an example of endothermic. And then we did this question here. And we said, look, it says activation energy. So that's from here to the top. That's that number minus that one, which was 222. And then the overall change was from here down. That's 389 minus 100, which is negative 289. And then we came to this. And this very, very hard idea, well, simple idea, but difficult to calculate, finished with us realizing that if we can find two routes, as long as we go in the right directions, we are okay. From Nairobi to Malindi or from Nairobi to Mombasa to Malindi, both are okay. And they will both be the same amount of energy in chemistry. And then we came across this example and those pieces of information there. And we needed to see that both the left-hand side and the right-hand side can be made from carbon and hydrogen. And that's where we end. Okay.